one of the important technical focuses of our University Defence Research Collaboration Phase 2, which has been sponsored by the Defence Science Technology Laboratory and Engineering and Physical Science Research Council, has been on cyber defence. Professor Jonathan Chambers is the director of the Loughborough, Surrey, Strathclyde, Cardiff and Newcastle Universities Consortium, and he has also been heading up a technical activity in the area of signal processing for cyber defence as part of this consortium, with support from colleagues in the Wolfson School of Mechanical, Electrical and Manufacturing Engineering at Loughborough University, namely Dr. Alex Gong and Dr. Kostas Kyriakopoulos, and a research associate, Dr. Francisco Aparicio-Navarro, from the School of Engineering at Newcastle University, but also hosted in the Signal Processing and Networks Research Group at Loughborough University. We have also enjoyed the support of key staff at DSTL to help in the development of our work. After my introduction, I will hand over to Fran to provide more technical details of our demonstrator. Our contribution has been to deliver a new system for communication network anomaly detection. In the military context, many battlefield applications can be modeled as complex networks of interconnected nodes representing objects or phenomena. The detection of anomalies in such networks can involve the detection of anomalies at both the node level and the node configuration level. But in this work, we consider the detection of cyber attacks at the node level. As such, we have focused upon network intrusion detection and have exploited unsupervised machine learning techniques to extract automatically key features from the network traffic measurements, thereby avoiding the limitation of supervised methods, which generally require the extraction of training data or signatures representative of a wide range of cyber attacks. Moreover, to improve the accuracy of the process of deciding whether an attack has occurred or not, we fuse the network traffic features with contextual information such as from a pattern of life model of expected network usage. Our system has the potential to handle both single and multi-stage attacks, and Fran will next provide a deeper introduction to our system and demonstration of its operation.
My name is Francisco Aparicio. I have been working as a research associate as part of the UDRC project since 2013, first at Loughborough University and currently within the School of Engineering at Newcastle University. My work over the last 5 years has been in the context of cyber defense and anomaly detection in communication networks. For the work I'm going to present, I have been considering multi-stage attacks and have designed a novel intrusion detection system which exploits contextual information in the form of pattern of life model and information related to expert judgment on the network behavior. I will demonstrate here the system operating in real time with real network traffic detecting a 5-steps attack. A multi-stage attack presents different characteristics than traditional cyber attacks. It requires the implementation of multiple stages. All these stages are essential for the successful completion of the multi-stage attack. One aspect that makes this type of cyber attack difficult to identify is that the various attack stages might not be malicious when implemented individually. Only when executed sequentially, the attacker could succeed in the completion of the multi-stage attack. Furthermore, the time between separate attack stages can span for hours, days, or months, making the detection of the multi-stage attack extremely challenging for most current intrusion detection systems. The cyber attack that we have implemented in our experiment unfolds as follows. There will be an initial passive reconnaissance stage in which the attacker would gather intelligence about the target. Then there will be a scanning stage comprising of 3 steps. First, the attacker will identify all active machines in the network. Second, the tool Mmap is used to identify open network ports in the target machine. Third, the attacker tries to identify exploitable vulnerabilities using the tool OpenBus. Next, during the exploitation stage, the framework Metaxploit is used to obtain the login credential of the target. It uses the technique called dictionary brute force SSH to give the attacker remote access to the target machine. Finally, a malware is installed also using Metaxploit during the last stage of the attack, namely post-exploitation stage. This malware will create a backdoor open in the victim machine, which can be exploited in future actions such as information exfiltration. The concept of pattern of life refers to the information generated by observing the network traffic over an extended period of time. This information would help characterize the behavior of the network and to determine if this behavior is anomalous. As an example, let's consider this graph that shows network traffic measurements gathered during 9 days from a network in a research office environment. We can see a periodic increase in the network usage during normal office hours from 9 to 5. This increase corresponds to the time at which researchers are at work accessing the internet and utilizing more network resources. These periodic changes would define the pattern of life model. As mentioned earlier, we have developed a novel unsupervised anomaly-based intrusion detection system. It is based on the combined use of various metrics from multiple layers of the protocol stack to carry out the detection. This is because when each step of the multi-stage attack is implemented, it is expected that the normal behavior of the network would be altered. The different attack steps would manifest themselves differently across all the layers of the network protocol stack. Additionally, this system uses the technique fuzzy cognitive maps to integrate the contextual information into the detection process. To evaluate the efficiency of this intrusion detection system, we have set up a real network testbed. The two main actors in this demonstration are the attacker, which conducts the multi-stage attack, and the victim machine, which runs the intrusion detection system. Additionally, the network traffic from various PCs at a research office environment is also monitored to generate the pattern of life model. The target machine monitors the network traffic and extracts a number of features to conduct the detection. The intrusion detection system would compute a level of belief on whether the current network traffic is malicious or not. This value is shown against time through a graphical user interface that we have developed using Python. As the different stages of the multi-stage attack are implemented, the level of belief in attack computed by the intrusion detection system will increase. Once the attack has stopped, belief in attack will decrease. To aid the work of cybersecurity analysts, this graphic user interface includes a visual indicator in red that flags where an attack is detected. A green visual indicator has also been included for evaluation purposes that compares the detection results with the ground truth. This novel intrusion detection system provides a highly effective solution to detect multi-stage attacks without previous training process. No such system is currently available in the open literature, and it's a solution provided by the UDRC2 through work at Loughborough and Newcastle University.